Hello everyone and welcome to this lecture 4 of our course on gas turbines and jet engines. Okay. So, in today's course we are going to study little bit revise the concept of Brayton cycle efficiency and work output. Then we will try to find whether there is an optimum value of this cycle. So, optimum value of the pressure ratio which gives us the maximum work output, and then we will try to solve a exercise problem which showcases the Brayton cycle calculations. So, just to have a quick revisit of what we had discussed in the previous class. So, in the previous class we have studied what is a Brayton cycle. So, as you can see from here, Brayton cycle consists of 4 processes. Okay, in the TS diagram, these are the isentropic compression process 1 to 2, which occurs in the compressor from 1 to 2. Then from 2 to 3 is the constant pressure heat addition. Okay. Then from 3 to 4 is the isentropic expansion, which occurs in the turbine, and we close out the cycle by using a constant pressure heat removal process. Okay. So, combining these 4 processes, we get a thermodynamic cycle, which we had discussed, that we call it as Brayton cycle. Okay. Assuming that all the processes are ideal, there are no internal losses, and this behaves as a air standard cycle. So, the properties do not change and air behaves as an ideal gas. So, with this we had derived what is the expression of efficiency. These were derived in terms of design parameters. So, what are design parameters? Design parameters are parameters which are defined before starting the design of a gas turbine. So, for this industrial gas turbine, there are 2 major design parameters. One is the pressure ratio R, which is the pressure ratio across the compressor. Second is the temperature ratio T, which is the ratio of the maximum temperature which occurs at the inlet of the turbine to the minimum temperature which occurs at the inlet to the compressor. Okay. So, these are the 2 main design parameters. We can also define a parameter called C, which is directly related to R, but it helps us in sometimes writing in a simplified form. C is defined as R to the power gamma minus 1 by gamma, where gamma is the ratio of the specific heat. So, this C is equal to T 2 by T 1, because T 2 by T 1, if we see from here, is equal to R to the power gamma minus 1 by gamma. So, now in terms of these design parameters, we generally calculate the performance parameters. Okay. What are the performance parameters? So, 2 performance parameters are important. One is the efficiency of this cycle or efficiency of the ideal gas turbine. This we had defined as eta. So, efficiency is denoted by eta, and this in the previous class we had defined it to be equal to W net by Q in, and we found an expression for this which is equal to 1 minus 1 by R to the power gamma minus 1 by gamma. Okay. So, we had seen that this only depends on the compression ratio apart from the type of gas which dictates what is the value of the ratio of specific heat gamma. But for a given gas, say for example, air, the only variable which influences efficiency is the compressor pressure ratio. Okay. So, we have seen in the previous class how we can generate plots for efficiency versus R. Similarly, we have also defined another parameter, very important performance parameter, which is the net work output per unit mass flow rate of a working fluid which is working on this cycle. Okay, per unit mass flow rate of the fluid, how much is the net work output from the cycle? This we generally put in non-dimensional form by non-dimensionalizing with the intake energy. So, we have defined this as W net by CPT 1. So, this was equal to Cp T 3 minus T 4 turbine work output minus Cp T 2 minus T 1 compressor work input divided by CPT1, from which we got an expression by cancelling the Cp values. We got an expression of this form T 1 minus 1 by C, okay, where C is as defined above, T is also as defined above, minus C minus 1. This we had defined in the previous class. Okay. So, now we can plot the variation with respect to T and C or T and R, as C is directly representative of R. So, we can plot this and find the variation of the net specific work output. Then we saw that how these performance characteristics look. Okay. So, we saw that the efficiency keeps on increasing for a given value of gamma, it keeps on increasing with increasing value of R. On the other hand, the work output, net specific work output, this increases up to a certain point and then it starts decreasing again. Okay. So, this means that there is a maximum value of work output which occurs at a certain optimum value of R. So, similarly, at a higher temperature ratio, say T equal to 3, we have similar maximum value of work output which occurs at a higher value of R, but still it exists. So, some optimum value of R exists which will be different than from for the case of T equal to 2, but after which again means if we keep on increasing R, the work output decreases. Okay. So, we want to find whether we can derive an expression for this optimum pressure ratio R, for which we get the maximum work output. Okay. So, that we will try to do in today's class before trying to solve a numerical example. By the way, before I proceed further, I would like to suggest that although we are deriving expressions like this, okay, for eta and for net specific work output, it is very important to remember that these expressions should not be directly used as formula for solving numerical problems. Okay. These are generally derived so that we can plot the performance characteristics for different design parameter values. So, how the design parameters affect the performance characteristics, but for calculation, actual calculation, as we will see today, instead of just using these expressions as formula, because if we do that things can easily go wrong, it is better to go with first principles and start to find the values of each of the state step by step. We will discuss this procedure in more detail towards the end of the class. So, now what is this optimum value of R? Okay. How can we find the optimum value of R and why does it exist? Okay. So, if we consider, let us say we consider a case like this, or even let us say that the case that is there on the left hand side. Okay. So, we see that we have a simple Brayton cycle going from 1 to 2, then 2 to 3, 3 to 4, 4 to 1. Okay. Within the same temperature ratio. So, temperature ratio why we are keeping same? Because the inlet conditions are fixed. Inlet temperature we do not have direct control, because it depends on the ambient conditions, so ambient air conditions, and the maximum temperature depends on the turbine blade material. So, that also we cannot directly control based on what is the cycle requirement. So, keeping T1 and T3 fixed, we can get various types of Brayton cycle by varying the compressor pressure ratio, compression ratio. For example, at one of the limiting cases, if the compression ratio is very large, okay, something like this, then we will get a very narrow cycle of this form. Obviously, the work output, which is the area within this cycle, let us say that this is 2 dash and this is 3 dash, within the cycle is very less as compared to the area work output of the previous cycle, where the area is clearly much larger within the cycle. Okay. So, it means that with higher compression ratio, we will go to a lower value of work output. Similarly, if we keep on now decreasing the compressor pressure ratio, say some value, intermediate value like this, the area will increase, we get a cycle like this. Okay. We get a cycle like this. So, let us say this is 2 double dash, this is 3 double dash. So, now we have a larger area, but still less than the original area. So, if we keep on decreasing the compressor pressure ratio, on the other limiting side, what we will get is a very thin flat like structure, very thin flat structure, somewhat like this. Whose area again is smaller than the original area. You can go to even lower values of compressor pressure ratio, we will get a thinner structure. Let us call this as 2 triple dash and 3 triple dash. So, we can see that there is a range of variation of the work output, starting from very small value going to a larger value and again going to a smaller value, when we are changing the value of R from the maximum possible value to the minimum value, which is equal to 1. Okay. It means that somewhere at a certain value of R, we will have a condition where the work output is maximum, and we want to find that. Okay. So, for that what do we do? So, we take the expression of the net specific work output W net by CPT1, that we have already derived, and that is equal to T 1 minus 1 by C, right, minus C minus 1. Okay. So, to get the optimum value of R, okay, to get optimum R, what do? We take a derivative of this net specific work output, or more correctly non-dimensional net specific work output. Remember that non-dimensional because we are non-dimensionalizing it with CPT1, net because this is the net work output. So, after removing the compressor work, and specific work output because this is per unit mass flow rate of the working fluid. Okay. So, non-dimensional net specific work output. So, this derivative of this with respect to R and equate it to 0 to get optimum value of R. Now, based on the variation that we have seen, we assume that this value minima or maximum, this will correspond to a maximum value of work output, because the minimum values are at the two ends of the range of R. Okay. So, this we can also take a derivatives in a similar way with respect to C instead of R, because C and R are directly related. Okay. And if we find the optimum value of C, we find the optimum value of R also. Okay. So, we can take d W net by CPT1 dC equal to 0. Okay. So, now using this top expression, we see that derivative of this with respect to C will give us minus of minus 1 by C square. Okay, one T is there. So, this will be T will be there, and then minus 1. So, this is equal to 0, okay, which means that T by C square is equal to 1, which means that C is equal to root T. Okay. C is equal to root T. So, physically what does it mean? It means that for our cycle, when this temperature ratio T 2 by T 1, which is equal to R to the power gamma minus 1 by gamma, which is equal to C, when this is equal to the root of temperature ratio T 3 by T 1, then we get the maximum work output. Okay. Let us simplify the previous equation further. So, we have obtained from the previous slide C is equal to root T. Okay. So, C equal to root T, which means that T 2 by T 1, C is equal to T 2 by T 1. Also, we know that P 3 by P 4 is equal to R. So, T 3 by T 4 is equal to P 3 by P 4 to the power gamma minus 1 by gamma. So, which means that T 3 by T 4 is also equal to C. Okay. So, this is also equal to T 3 by T 4. We have discussed this in the previous class also. This is equal to C, which is equal to root of T 3 by T 1. So, from this now, if we multiply T 2 by T 1 with T 3 by T 4, so C into C, okay, C into C. So, this should be equal to square of root T, so which is T, which is equal to T 3 by T 1. So, T 1 and T 3 gets cancelled from both the sides, and we are left with a very nice expression T 2 equal to T 4. Okay. So, for maximum work output, the temperature at the exit of the compressor, this temperature T 2 should be equal to the exhaust gas temperature at the exit of the turbine. If these two are at the same temperature, how we will get them at the same temperature? By varying the compressor pressure ratio. So, we should have such a compressor pressure ratio such that T 2 equal to T 4, and then we will get the maximum work output. Okay. So, for example, if I just consider some numerical value, okay, for example, for T equal to 5, okay, let us say that the inlet temperature is 300 Kelvin, the maximum temperature is 1500 Kelvin, all are realistic values. So, in that case small t is equal to 5. So, we get that for optimum value C optimum should be equal to root 5, okay, root T, which is equal to root 5, which gives us a value of optimum value of R. Remember that R is nothing but related to C, such as C is equal to R to the power gamma minus 1 by gamma, or R is equal to C to the power gamma by gamma minus 1. So, this is equal to 16.72. So, for this temperature ratio, if we take a pressure ratio of 16.72, which is a reasonable pressure ratio, we will get the maximum work output from the cycle. This does not mean that we get the maximum efficiency. Remember that we had seen that efficiency keeps on increasing with R, okay, but the work output decreases. So, what is the significance of this? If the work output is maximum, it means that for a given mass flow rate of air or working fluid, we get the maximum work output, or the other way around, if we need a certain amount of work output, we will need the least amount of mass flow rate of the working fluid, which means that our device will be will have the smallest possible size. Okay. So, considering both efficiency and work output, what is done is that a value of R is selected such that it is near to this optimum value of R for significantly high values of T, such that we get good efficiency also, but we do not also compromise on the net specific work output. So, I hope this is clear. Okay. So, then let us now try to solve a numerical example. The purpose is twofold. One is to understand how to solve this type of problems. Second is to see for realistic cases what type of values are obtained. So, we should get a feel for the values, because if you are studying this topic, you should know what are the like various values or ranges of values associated with each parameter, what are the different characteristic values. We should have a good intuitive feel for that. Okay. That can be developed by solving problems where the problem values are taken to be realistic. Okay. So, Brayton cycle calculation example. So, I will write the problem here directly. So, we have a Brayton cycle, ideal Brayton cycle. Okay. Till now we are only considering ideal Brayton cycle. So, ideal Brayton cycle and its inlet condition unknown, which is also going to be the case for a real life design. So, we will know at what ambient condition this gas turbine will operate. Okay. So, inlet condition which is equal to T A, we write it as T A. So, in this case that is equal to T 1. Okay. So, ambient T 1 is equal to the ambient condition T A, which is say 300 Kelvin, and the inlet pressure P 1 is equal to the ambient pressure P A, which is equal to 1 atmospheric pressure. It is also given that what are the values of the design parameters. So, design parameter pressure ratio R has a value of 10 and the maximum temperature that occurs in the cycle, that has a value of 1500 Kelvin. Remember that based on our definition of temperature pressure ratio, this means that T is equal to 1500 by 300, which is equal to 5, okay, temperature ratio of 5. Typically, we will know what is the maximum temperature of possible in the cycle, because as I had said previously also we had discussed, this depends on the material of the turbine blades. Okay. So, the turbine blades have to withstand a high temperature, and depending on their quality we define what should be the maximum temperature in the cycle. Okay. So, this anyway we will discuss later on when we discuss turbines specifically. So, now coming back to this problem. So, ideal Brayton cycle we will consider air standard cycle. Okay. We will consider air standard cycle. So, ideal gas air, and we will take the following properties. Okay. So, in general for all these air standard cycles we will stick with these property values. Cp we will consider for air to be equal to 1.005 kilojoule per kg Kelvin. In real life this Cp value will change with temperature, it also changes with composition. For example, after combustion the Cp will be different, but when you are considering then the entire cycle is based on air, then we can take a constant value of Cp, which in this case is equal to the standard value 1.005 kilojoule per kg Kelvin. Gamma for air is equal to 1.4. Okay. In this case R is not required, specific gas constant, but in case it is required in some problems we will take it as 0.287, again standard value for air. So, R is the specific gas constant which is equal to the absolute gas constant or universal gas constant divided by the molecular weight of air, okay, 0.287 kilojoule per kg Kelvin. So, now we want to find out. So, what do we want to find out? We want to find out what is the efficiency of this cycle or of this turbine and what is the net specific work output of this turbine. Okay. Efficiency of this turbine and net specific work output of this turbine. So, how do we proceed? So, in all these type of problems, the first step is always to start by drawing the TS diagram. Okay. So, we will start in the next slide. Okay. So, I am pausing, or you can pause here for a minute just to read through all the given conditions. Okay. So, now for starting the solution, we will start with a TS diagram. Let us draw it on the right hand side. This will be the first step for solution of all types of gas turbine problems, because this gives us the idea of how the cycle proceeds. Now, we have the 4 processes going from 1 to 2. Remember the important thing that we have discussed, that we will not use the expressions derived previously as formula. We will start with first principles and try to calculate the value of temperature, and if any other variables are required at each of the states, okay, after each of the processes. So, this is the TS diagram. 1 to 2 is the compression, isentropic compression, 2 to 3 is the constant pressure heat addition, 3 to 4 is the isentropic expansion, and 4 to 1 is the constant pressure heat removal. Okay. So, now we can do very simple calculations. T 1 by T 2, we already know this should be equal to R to the power gamma minus 1 by gamma. Remember, R is equal to P 2 by P 1. So, here we have taken R to be equal to 10, or it is given to us that R is equal to 10. So, 10 to the power 0.4 by 1.4. Okay. So, this comes out to be equal to 1.9307. You can pause and do the calculation, okay, and find the value of T 2. So, with this value of R, the value of T 2 comes out to be equal to 579.21 Kelvin. Okay. Again, I encourage you to parallelly do the problem, pause and parallelly do the problem, and then try to verify the result. Okay. So, similarly, T 3 by T 4, this we know that this should be equal to 1 by R to the power gamma minus 1 by gamma. So, this is equal to 1 by 1.9307, okay, which means that T 3 is known. Remember, T 3 is 1500. Okay. In the first case, T 1 was known. So, here T 3 is known 1500. So, we get the value of T 4. T 4 comes out to be 776.92 Kelvin. Okay. So, we have found the temperature at all the 4 states. T 1 equal to 300 Kelvin, T 2 equal to 579.21 Kelvin, T 3 equal to 1500 Kelvin, and T 4 is equal to 776.92 Kelvin. Very important point that we should remember here, although it is very basic, is that remember to use the values in Kelvin when you are doing these calculations. T 1 by T 2 is equal to P 1 by P 2 to the power gamma minus 1 by gamma, all these ideal gas calculations. Use the calculations or do the calculation in terms of temperature expressed in kelvins, okay, otherwise the results will be incorrect. So, now from here we see that the work output of the compressor, work input to the compressor, it should be equal to C p T 2 minus T 1. C p we are going to take as 1.005 kilojoule per kg Kelvin. We have already obtained the value of T 2 and T 1. So, this comes out to be equal to 280.61 kilojoule per kg. Okay. Kilojoule per kg here represents that this is the work input required when the mass flow rate of the working fluid is 1 kg per second. Okay. So, for unit mass flow rate, what is the work required? Okay. Similarly, for the turbine, we can easily find what is the work output C p T 3 minus T 4. So, replace the values and you will get value equal to 726.69 kilojoule per kg. So, net work output in that case is equal to W t minus W c, which gives us a value of 446.08 kilojoule per kg. To find the efficiency, so this is one of the answer, the net specific work output per unit mass flow rate. Then the efficiency, for efficiency we also need the value of Q in. Q in again is equal to, for the process 2 to 3, this is equal to C p T 3 minus T 2. By the way, how this work output, heat input we are expressing in terms of C p into delta T. So, this comes from the energy balance, that W c is equal to H 2 minus H 1, W t equal to H 3 minus H 4, that H can be written as or delta H can be written as C p into delta T. Okay. Anyway, so Q in is equal to C p T 3 minus T 2. So, this again replace the values and you will get this to be equal to 925.39 kilojoule per kg. Thus, finally, the efficiency, which is equal to W net by Q in, comes out to be equal to 0.482. Okay. 48.2% for the simple cycle, because this is ideal. In general, for a real cycle with this simplified form, considering all losses, the efficiency will come down to a much lower value, in the lower 30s percentage probably. Okay, here it is 48.2%. Just let me correct this one. Okay. So, just a few points before we end the class. So, one is that see the value of turbine work output and compressor work input. Okay. So, the compressor work input is a significant fraction of the turbine work output. So, for gas turbines, a significant amount of work which is generated by the turbine goes for just running the compressor itself. Those of you who have studied power plant engineering or steam turbines might have noticed there that the compression process requires very less amount of work, because it is done in liquid state, whereas the turbine work output is orders of magnitude higher as compared to the work required for compression. So, unlike that, for gas turbines we have compressor work requirement, which is a significant portion of the turbine work requirement. Okay. So, this is important, and that is why the efficiency comes down, and there are ways to mitigate this to increase the efficiency. There can be modifications done to the cycle, which we will see in the subsequent classes. Okay. Also, take a, again I would suggest that you pause here and take a look at the values, because these are all realistic values that we are using and obtaining. So, this will give you a feel of the type of values involved in this type of calculation. Okay. So, with this we will quickly summarize what we have done in today's class. We have learned how to what is the Brayton cycle efficiency and work output, okay, what are the expressions for this, derived an optimum value of the pressure ratio, and then finally, we have solved a numerical problem for Brayton cycle and tried to understand the various calculation procedure as well as the numerical values involved in this type of calculation. So, these are the references, mainly the important books based on which this course is developed. Okay. And one image has been taken here from Wikimedia Commons under license of means sharing license. So, with this I thank all of you, and we will meet in the next class again. Thank you.